Hello, my name is Aiden Riley, and this is my lab report on Lab 6 Magnetic Molasses. The purpose of this lab was to compare the observation of a bar magnet falling through a conductive tube of aluminum foil to a simulated model of the same situation. In the real model, it took 0.985 seconds for the bar magnet to fall through. In the simulated model, 0.398 seconds. Some important principles and equations to know: the Biot-Savart law to calculate the magnetic field, which we then use the magnetic flux formula to get the magnetic flux with that same magnetic field. We then use Faraday's law to get the voltage, uh, which we then use Ohm's law to translate that voltage into a current, which we can then turn into a magnetic current, which we can then turn into the magnetic force of the ring on the bar magnet, which will then use the Lorentz force equation to turn that into the magnetic force. The experiment itself: bar magnet, 47 centimeter length tube of inner radius 3.175 centimeters and outer radius 3.8 centimeters, and a camera. The system is the tube itself and the bar magnet. The surroundings is everything else. Our average time was 0.985 seconds. Our code starts with the constants. The top left is our universal constants. The top right is the dimensions of the tube. The second to bottommost block is the mass of the bar magnet, the magnitude of the dipole moment, and the bottom is just the visualization of the bar magnet. Next is the dipole and flux calculations. First, we use the Biot-Savart law to calculate the magnetic dipole of the bar magnet. Then at the bottom, we use the magnetic flux equation, particularly tailoring to the model as a ring, like sections of ring over time. And that is where we get our magnetic field and area portions for this particular part of the calculation of magnetic flux. Next, we have the iteration and forces part of the code. The iteration block on the left just allows us to track the motion over time. On the top right is our ring current, which we then, as explained earlier, will turn that current back into a magnetic current, which we will then turn into a magnetic force. Um, Turning that magnetic force, we then add that magnetic force produced by the ring to the magnetic force of the magnet itself to get our total magnetic force, which we then vectorize and add to the gravitational force to get our total summation of forces, get our acceleration, our velocity, and allow us to track the motion of in our computational model. Speaking of the computational model, here is the simulation. As you can see, there's a blue and red portion of the bar magnet falling through the tube. The blue portion would be the counterclockwise current, and the bottom red portion is the clockwise current. We know this because the magnetic flux is decreasing and pointed downwards, and we can backroute to understand what the directions of the different parts of the bar magnet, the magnetic north and magnetic south, would thus be. If we flip the magnet around, then the blue part, if it was still on the top, would be clockwise, and the red part, if it was still on bottom, would be counterclockwise. Um, and that would just be that. The total time of the real to the computational, the real is about double the computational. This is most likely because of human error plus not accounting for drag forces in the computational model. The shape of the velocity versus time graph just tells us that there's an acceleration due to gravity despite the presence of the magnetic force. Our two what ifs: if the resistivity was to go to near zero, the current would be extremely high, increasing the magnetic force significantly, magnitudely at least. The second what if would affect the direction of the magnetic force, particularly when there's these holes or gaps. The magnetic force vector wouldn't be directly up, which means that the magnet would then start spinning or rotating in both like the theta and phi directions, I guess, and that would result in a non linear fall simulation.